Okay, and welcome to the next video where we're looking at logarithms. So building on the previous video where we looked at the first rule of logarithms, going from exponential form to log form and vice versa. And now we're going to look at some laws of logarithms, which again are very important and you need to remember throughout the Year 12 course and indeed going into Year 13. So what are the main laws of logarithms that you need to understand? Well, the most important thing before we get into this is that the base of these logs have to be the same. You cannot do any of these laws until the base of these logs are the same. Okay. So the first law is multiplication law, which basically means if you've got the log of a value x and you're adding the log of a different value y, as long as their base values are the same, you can multiply the contents of the log. Okay. And numerically, if you apply this law, as long as the base is the same, numerically this does work. Okay, and obviously it does the theory behind it is based on indices, which I'm not going to go through in this video. So that's multiplication law, and this works either way. You can break up a log with a product of two different numbers back into this form. So indeed, you can go back into you can go from there to there or there to there. That's really important. Multiplication law because you're multiplying x and y, these two different numbers, which were originally being added inside the logs. The next one is division law, which basically means when you subtract two logs with the same base and you've got different numbers inside them, you can divide the contents of the logs. Log base a x over y. Okay, so again, you can go from there to there, and if you've got a log of a fraction, you can rewrite it in that form. The other really important law is the power law. Okay, and power law basically states that if you've got power in the inside of your log, inside value of your log, then you can bring down that power to the front of the log. Okay, so again, if you've got power on top of the value of the log, you can bring that in front of the log, and you can rewrite that in either way. Okay, so those are the laws which you need to remember, really important. And here are some useful sort of tips as well. So you've got log base a, that's always equal to 1. So if you've got the log of a number to a base, and if you've got the same number here, that's always equal to 1. The reason for that is, if you're to rewrite that in exponential form, you get a to the power of 1 equals a. So that does work. Okay. Similarly, if you've got log base a to the n, then that's just going to be equal to n. Why? Because you can bring down the power in front of the n log a, and you know that's equal to 1, so it's just n. It's a typo, it's the same thing. If you've got log of 1, that's always equal to 0. So any log to any base, if you've got a 1 inside the log, that's always, the value is always equal to 0. Again, if I was to write an exponential form, you'll get this, a to the power of 0 equals 1. Okay, so that checks out as well. Right, so again, we've just gone through the laws, we've gone through the useful things. The final thing in the notes box that is quite important is this. So if you've got log of a number equals another value, you can rewrite it in that form. So basically talking about going from log to exponential. Okay, so it's that rule from the previous video. It can be used to help you solve equations. Right, so we've got quite a few questions here that we need to work through. Let's just work through them. So, rewrite as a single logarithm, a quarter log a4 plus log a6. Now, what you've always got to look at with these questions is, okay, I've got a plus between two logs, so I could use multiplication law, but I've got this half in front of log a4. And within multiplication law, you can't really deal with that half at the moment. But if I've got a number in front of a log, I could use a different law, which is power law. Okay, a number in front of a log can be rewritten as the power of the value inside the log. So half log a4 can be rewritten as log a4 to the power of a half. Okay, they're the equivalent value, plus log a6. Now log a4 to the power of half is log a2 plus log a6. And when you're adding two logs, if the bases are the same, then you can multiply the contents of the log. So you get log a12, and that's it. So let's just recap the skill. You've got a number in front of a log. It's best to rewrite that as a power of the value inside the log, because you can use power law, and then you can then do multiplication law after that. Right, question 2. We've got a situation here. We've got log base 3, 5 equals c. Find in terms of c these values. Now students find this quite difficult because you've got a situation where they're giving you some information, but it's not immediately clear how you get to these other values. Okay, so first of all, let's look at log base 3, 5 equals c. Okay, so if I see log base 3, 5, that's always equal to c. Now log base 3, 15, I need to rewrite that in terms of c. The only way I can rewrite that in terms of c is if I've got log base 3, 5 somewhere. Right, log base 3, 15, how can I rewrite that? Is there a way of rewriting 15 in terms of 5? Yeah, 3 times 5. Okay. Now, if you've got two numbers being multiplied, that must mean, using multiplication law, log base 3 times 5 can be rewritten as log base 3, 3, plus log base 3, 5. Okay? And if you remember the useful hints that we've got on the top of the box here, log base 3, 3, that has a value of 1. And log base 3, 5, that has a value of c. So part A can be rewritten as 1 plus c. Okay, all we've done is we've sort of thought to myself, okay, how can I rewrite 15 in terms of products, and then how can I use my knowledge from there? Right, next one, log base 3, 0.2. Now 0.2 is the same as 1 over 5. Okay, so I can rewrite that. And I've now got log base 3 of a number over another number. Now using division law, I can rewrite that as log base 3, 1 minus log base 3, 5. They're equivalent values, okay? I'm just using division law. Now again, if you look at the useful hints that we've got at the top, log base 3, 1, that value is just 0. So you're left with log base 3, 5 with a minus in the front, and that's going to be minus c. Okay. Okay, final one, c, got log base 3, 125. How am I going to get that in terms of log base 3, 5? Well, 125, I know that that's 5 cubed. Okay, so I know that I could use that to rewrite 125. Now, once I've got 5 cubed there, you've got to think to yourself, how am I going to deal with that? Well, power law states that if you've got power in the value of the log, you can bring down that power in front of the log. And log base 3, 5 is c, so you're going to get 3c. Okay? So, that's question 2. Just using laws of logs to rewrite things in terms of letters. Right, now we're getting on to things which are definitely A-level in nature and require sort of a high-level skill set. We've got to solve this equation. Log base 10x plus 5 log base 10(2) equals 2 log base 10(4). On the face of it, this does not look nice. But if we just stay calm and realise, actually we can simplify this, then it won't be too problematic. So log base 10x, you can't really simplify that any further. But you've got 5 log base 10(2). You've got a number in front of a log. And if there's a number in front of a log, it's always best to bring that number up as the power. So instead of 5 log base 10 2, I'm going to write log base 10 2 to the power of 5. Similarly, I've got this 2 outside of this log, so I'm going to write this as log base 10 4 squared. So let's just tie this up a bit. Log base 10x plus log base 10 2 to the power of 5. Now 2 squared, 2 cubed is 8, times 2 is 16, so you've got 32. And then 4 squared is 16. Okay. Now remember, what do we want? We want to solve, so we want to get x equals. So anything to do with x, I'm going to keep on one side. Anything which isn't to do with x, I'm going to keep on the other side. Okay. Now I've got a minus between logs. If I've got a minus between logs, I'm able to divide the contents of those logs. Division law. Okay. And you get log base 10, 16 over 32, which is a half. Now most students at this stage, they cross out the log base 10s, and I always advocate that we don't do that, because that sort of gets into bad habits. You should never cross out logs in this manner at all. What you should understand is I've got two logs that are equal, and if they're equal to each other, and it's in the most simplified form, and the bases are equal to each other, then that must mean the contents of these logs are equal to each other. So we can say that x must be equal to a half. Okay, so let's just recap that again. To solve this equation, I simplified any logs using any rule that I need to. I then tried to isolate any log which has got x on it onto one side, and everything that hasn't onto the other side, simplifying that. I then simplify it to one final stage to make sure there's no other complications. I think to myself, okay, these two logs are equal, the bases are the same, therefore the values inside the logs must be equal. Right, question 4. Solve the equation log base 3 4 minus equals minus all that. So again, I've got minus 2 outside the log base 3. There's a variety of ways I could do this. I can put that minus 2 as a power of x using power law, and keep the plus 2 there. Now, I'm going to subtract the 2 because I don't want that there anymore. Again, said like I wanted to try and get the log with the x isolated on its own. Okay. So what I need to think about here is how can I simplify this left-hand side further? Now at the moment I've got log base 3 4 and I've got 2. Is it possible to find a value log base 3 something which gives us a value of 2? Because remember, log base 3 is what I want. Until I get every single log with the same base, I can't really manipulate any further. Okay, so let's just have a think about this. Log base 3 of a number x equals 2. Okay, what would that number be? Log base 3 of a number x equals 2, because I want to replace 2 with that expression. Now, if I use my rule from the previous video, that must have meant that 3 squared is equal to x. Yeah? So I'm going from log form to exponential form. That must mean by x is equal to 9. So, in this question, I can replace the 2 with minus log 3 9. Okay, because that has a value of 2. Now, this left-hand side, I've got to subtract between two logs with the same base. I can write that as 4 over 9. Okay. And remember, I've got two logs that are equal to each other. They're in the most simplified form. Their bases are the same, so I can make 4 over 9 equal to x to the minus 2. And x to the minus 2 is 1 over x squared. And if you were just to use a bit of algebraic manipulation, x squared equals 9 over 4. And therefore x is equal to 3 over 2. Now, you might be thinking, why is it not also minus 3 over 2? The issue is that if you would substitute minus 3 over 2 into that, it wouldn't actually work. The log graph does not accept negative x values. It doesn't exist. So when we do square root and we get two x values, you can only have one of them. 3 over 2 here. Okay? Right. Going on to the next page then. Now we're going to use logs again in a slightly different way to solve these equations. And we just have to be mindful again of what we're doing using the appropriate laws. So we've got to solve the following equations to 3 decimal places. So we need our calculator for this. I'm just going to get mine out. Okay, so we've got 3 to the power of x equals 20 and 5 to the power of 4x minus 1 equals 61. So in the previous video I said that it's very useful to be able to use the rule from getting from exponential to log form or log form to exponential form for this sort of context. Why? Because you know 3 to the power of something gives you 20. We know that 3 squared is 9 and 3 cubed is 27. So we know our answer is between 2 and 3. And logs can help us get the exact value to a certain degree of accuracy. And this is how we use it. This is how powerful logs can be. So 3 to the power of x equals 20. This is exponential form. I want to get this into log form. And to do that, I'll recognise that 3 is going to be the base of my log. 20 is going to go and become the value inside of my log. And x is going to be the unknown value. I then solve this by using my calculator. So I press log button here. And I type in exactly what I need. So I'm going to type in 3 as the base, 20. I get 2.7268. But to 3 decimal places, that's 2.727. And that agrees with what we were discussing or thought about earlier, that the power has to be between 2 and 3. It's going to be closer to 3 than it is to 2. And using logs is very powerful. It can help us get that power to a certain degree of accuracy. So part B, I'm going to use the same skill. 5 to the power of 4x minus 1 equals 61. So that's exponential form at the moment. I'm going to go into log form. So the base will be 5. 61 will be the value inside the log. And 4x minus 1, the whole of that power will go onto the right hand side. Now, the value of x, you just solve to make x a subject. So you go log base 561, add 1, and then you divide through by 4. So let's set that up then. We'll do a fraction, log base 561 plus 1 over 4. Get 0.888, etc. But to 3 decimal places, 889. Okay, so that works out. Okay, so that's how we use logs to solve equations where with unknown powers. Question 6. Got to solve this equation. Now, on the face of it, again, it looks quite difficult. How are you going to solve that? It's not easy looking at it. But if I was to break this down using indices, it can actually be done relatively easily. The key is understanding 5 to the power of 2x and how you can rewrite that. So 5 to the power of 2x, there's another way of rewriting that using indices. 5 to the power of x squared. Yeah, because when you multiply these two powers, you get 2x. Now, 5 to the power of x squared minus 12 times 5 to the x plus 20. So let's just repeat that again. You've got something squared minus a number, that's something, plus 20. That sounds like a quadratic. And indeed, it is a quadratic, but it's just got 5 to the x instead of a letter. So what you can do is you can either factorise as it is. I prefer to rewrite 5 to the x in terms of a different letter, so I'm going to use, I don't know, y. At least that helps me visualise the quadratic a lot easier. Just going to write it here, let y equal 5 to the x. Okay. Now I'm going to factorise this. I'll get y. Now two numbers that I multiply to give you 20, but somehow add to give you 12, so it's going to be something to do with 10 and 2. So minus 10 minus 2, y equals 2 and 10. But remember, we don't really care about y, we want 5 to the power of x equals these two. So you've got 5 to the power of x equals 2, and 5 to the power of x equals 10. Now, we've just done something similar in question 5. You've got 5 to the power of something equals 2. How can we use logs to do that? Remember, I can rewrite this in log form, this exponential form. So log base 5, 2 must be equal to x. And similarly, log base 5, 10 must be equal to x. And when you turn your calculator to 3 decimal places, get log, you get 0.431. Log base 5, 10, 1.431. So again, this type of question on the face of it looks quite difficult, but there is a technique to solving it, and it just requires you to understand indices. Okay, right, final couple of questions, then that's it for the video. Just this one here, so this is again where the skill set gets more difficult. As you can see, as we're progressing through these 2 pages, things are getting more difficult. So again, we've got to solve this equation. You've got an exponential 3 to the x, and it's equal to another exponential. Now, again, on the face of it, you know, you've got 2 graphs that are equal to each other, and we need to find the value of x for where they intersect. How do we use logs to solve this? You can't really convert both of them into log form, okay, because they're both exponentials. Well, what you can do instead is sort of think to yourself, okay, if they're both equal to each other, and obviously, you know, the values are both equal to each other at a certain point, then what you can say is the log of these values, the log base 10, must be equal to each other as well. Okay, and it sort of goes back to the previous questions when I said to you to never cross out logs. You know, if they're equal in the most simplified form, then you can say that the contents of logs are equal. So I'm just using that technique. Once I've got to this stage, once I've applied logs to both sides, which is what we say in A-level maths, I can then break things down a little bit. I've got powers here. Remember, we want the value of x. So if I bring down the power, log base 10, 3, I bring down this power, x plus 1, log base 10, 2. Yep. Now get to this stage. Now I'm going to expand the brackets with x plus 1 and log base 10, 2. Okay. I'm going to bring everything to with x on the left hand side. And everything to not with x on the other side. Remember, you know, when we try and solve equations, we want to make sure we're getting through to the x on one side. Factorise out the x. And then divide through by that bracket. When you do that in your calculator, log base 10 2 over log base 10 3 minus log base 10 2, you get 1.7095 to 4 decimal places. Okay, so that's how we do that question. Right, final question on the sheet, and as you can see, we've used the laws of logarithms quite extensively. We're coming to the final question. Got a situation here, we've got money being invested in an account, and it increases at an interest rate of 6% per year, with an initial investment of £400. Write down an equation to model the amount of money in your account in terms of t. So M, I'm sort of thinking about this in terms of interest rate. If you've got £400, okay, and it's increasing by an interest rate of 6%, then year on year it's going to take on a value which is 1.06%, 1.06 times its original value. Okay, so I mean we can do that manually as well. So 400, 0.06, £24. So it gains £24 in interest. So you get 424. How can I get to the answer really quickly? 400 times 1.06. There. So after the first year, it's £424. So the general formula will be 400 times 1.06 to the power of t. T being the number of years. Part B, find the amount of money in your account after 5 years. So when t equals 5, you get £535 and 30p. Okay. And part C, find how long it will take to double your investment. So if you invested £400, then double of that investment will be £800. So essentially they want the value of t, which makes this equal to 800. So let's divide both sides by 400. I've got 1.06 to the power of t equals 2. Hold on, that's an exponential. So if that's exponential form, I can write that in log form. Log 1.06, 2 equals t. Therefore t equals log 1.06 to 11.895 years. So it won't take 11 years, because if you say 11 years, it wouldn't have doubled money by then. So it definitely take 12 years to double it. Okay. Right, so that is laws of logs finished, and you can see the skills that we've had to use. So I'll just quickly recap that. Multiplication law, division law, power law, some of these useful notes, writing in single logarithms, writing in terms of other logarithms, solving equations, solving slightly harder equations, solving equations in exponential form, and solving equations in a sort of quadratic exponential form, solving equations with quadratic exponentials equal to each other, and solving a context-based exponential question. So I'd highly recommend having a go at these questions on these pages, and that's the end of the video.